Welcome to this course on working with Unicode in Python. If you've done anything beyond basic text processing in Python, or had programs that worked with lots of textual data, it's likely that you've run into various Unicode-related errors. And if, as is increasingly common these days, your programs need to deal with expanded character sets or multilingual data, then you're bound to run into these sorts of problems eventually. Let's begin by talking about who would benefit from this course. This course will be useful for you if you don't know much about Unicode or only have a basic understanding of it, and if you find yourself perplexed and frustrated when faced with issues such as Unicode encode errors and Unicode decode errors. More specifically, much of what we'll cover will be useful if you have software that does lots of text processing and needs to be ported from Python 2 to Python 3. And this course will also help if you have software that was originally written with a single language in mind, let's say English, but which now needs to be adapted for a larger audience or for multilingual datasets. The overall goal of this course is to show you how to make effective use of Unicode in your Python programs. This means helping you avoid Unicode-related problems to begin with, but also giving you what you need so that you can understand any problems that crop up, and beyond that, implement solutions for those problems. You'll also learn how to deal with some of the added complications of working with Unicode text. Here are some of the topics that we'll cover. You'll gain a solid foundation in character encoding generally, and Unicode in particular. Such a foundation is extremely useful no matter what sort of work you're doing with textual data. You'll gain a clear understanding of the differences between text strings and byte strings in Python. You'll learn when to use each type of string, how to convert between them, and how to handle conversion errors. You'll also get some recommendations on how best to work with Unicode data. By following these principles, you'll be able to avoid many of the usual difficulties. And finally, you'll learn how to deal with some of the special challenges presented by Unicode text. In particular, we'll look at how you deal with string comparison and sorting. In this course, I'll assume that you have a basic familiarity with Python. Knowledge of advanced language features will not be needed for the topics we'll be looking at. By default, I'll show you how to work with Unicode data in Python 3, but as we proceed, I'll also explain how to do the same things in Python 2. The important differences in string handling between Python 2 and Python 3 will also be covered, and beyond this, 2 lessons are devoted to special issues in Python 2. This course is ultimately intended for practical application, but it differs from similar treatments in that we go a bit more in-depth on some fundamental concepts. Specifically, I want to offer a solid foundation in character encodings and Unicode, along with Unicode character encoding schemes. We'll also give a bit more conceptual background when it comes to character equivalence and normalization. Having a good understanding of these topics will be useful when working with Unicode data, regardless of the programming language that you're using. As I said, however, this course ultimately has a practical focus. It should equip you to write Unicode-aware Python software, to ensure that Unicode data is being handled properly, and to avoid Unicode-related problems as much as possible. The material in this course is informed by my own experiences using Python in humanities-related research and teaching. And as such, I hope you will find the course applicable as well as illuminating. In this video, we will look at the software setup that I'm using in this course. The course content remains independent of platform, editor, and shell, so you're free to use whatever setup you like. What I present here is simply offered in case it helps you follow along as we go through the course. All of my examples are presented in Windows. Instead of using the Windows command prompt, I am using the bash shell and min-tty terminal that come bundled with the Git for Windows distribution. Not only are these tools more powerful than the standard Windows command line, but they will also look more familiar if you are working in OS X or Linux. Also, because the software comes bundled with Git, it is readily available and easy to set up. With regard to the Python versions used, our main focus here is Python 3, but we will also look at Python 2. On my system, I have both Python 3.5 and Python 2.7 installed. Python 3 is used by default. When necessary, the Python launcher for Windows utility, or the py command, can be used to specify Python 2. For convenience and clarity, in my environment, I've set up an alias called Python 2. Because we are working with Unicode text, it's important to use a font that provides good Unicode coverage. That is to say, a font that includes representations for the characters that you are likely to encounter. Beyond this, you want a font that is visually clear and suitable for programming. Let's look at some possibilities. First, let's open a sample file. Here, Marcus Kuhn's utf8 demo.txt. This demo file is helpful for giving a rough sense of what a font covers and how it will render. Finding a font that rendered everything in this file correctly would be pretty difficult. For our needs, let's just take a look at the section that demos plain text typography. Currently, we are looking at the text with the font Courier New. Of the monospaced fonts out there that have reasonable Unicode coverage, here are some recommendations. Keep in mind that because we are focused on monospaced fonts here, we have a more limited range of options than if we were looking at variable width fonts. First, we have Deja Vu Sans Mono from the Deja Vu family of fonts. Another good font is Ubuntu Mono. And for those who prefer a bitmapped font, GNU Unifont is also an option. On my system, I need to set the font size to 12 to have Unifont render clearly. In this course, I am using Ubuntu Mono in both the editor and the terminal. My preferred text editor is Vim. You are of course free to pick whichever editor you find most usable and productive. When you're working with Unicode text, most text editors have helpful features that make this easier. Here are some of the functions that I find most useful in Vim. Oftentimes you want to type in a character, but your keyboard doesn't support it. If you know the character's numerical value, that is to say its Unicode code point, you can type it in using Ctrl-V-U. Here's how it works. In insert mode, press Ctrl-V, then release and hit lowercase u. After that, you type in the 4-digit hexadecimal code point for the character. For example, let's use this command to enter a capital Greek letter pi. The character's code point is hexadecimal 03A0. I go into insert mode, press Ctrl-V, then U, then 03A0, and the letter appears. By the way, if you are inserting a character whose code point does not fit into 16 bits, use Ctrl-V followed by an uppercase U. Now let's say that you want to know the code point or numerical value of a character. Place the cursor over the character and press GA. Let's check the code point for the capital Pi that we just entered. I'll press GA over the character here, and down at the bottom of the screen, you'll see the code point, 03A0. Usually we will store and transmit Unicode text as UTF-8. You can use the G8 command to see the UTF-8 byte sequence for the character under the cursor. Once again, let's try this on the capital Pi. Here, with the cursor over the character, I'll press G8, and then we will see the byte sequence, CEA0. As I mentioned, most editors have similar features, so it may be worth investigating to see what helpful functions might be available in your preferred text editor. In this video, I'll discuss two configuration issues that may be relevant if you are using Python on Windows. The first issue applies if, like me, you are using the min-tty terminal and not the Windows command prompt. As of this recording, there is an unresolved issue between min-tty and Python. This issue shows up when you run Python without any arguments in order to enter interactive mode. As you can see, if I run Python without any arguments, nothing seems to happen. The workaround in such cases is to run Python with the winpty command. In fact, if you are using min-tty, it's best to always run Python with winpty. In the environment that I'll be using as we proceed in this course, I've set up aliases to make sure that Python is always run with winpty. Here are my aliases. You can also find these in the working files. I disabled these aliases in the current session for demonstration purposes, but now I'll restore them. The second issue relates to Unicode input and output on the Windows console. This also applies if you are using min-tty. The Python interpreter running on Windows is pretty limited when it comes to reading and displaying Unicode characters. Fortunately, there is a package called WinUnicode Console, which works around many of these problems. The easiest way to install the package is with pip. Let's see what this package does. Take, for example, a string containing the euro symbol. This character has code point 20AC. By default, I cannot enter the character directly. Python couldn't handle the input and replaced the character with a question mark. The \u escape sequence will work. Attempting to print the string does result in an exception, however. This is because standard out can only handle CP437 for output. Now, there's really no reason why we should be limited in these ways. WinUnicode Console fixes these issues. Here's how we enable it. And now our previous attempts will work fine. This is convenient and makes things a lot clearer, so you probably want to have WinUnicode Console enabled by default. To do this, you can add the call to winUnicodeConsole.enable to your user customize module. First, let's find out where the user customize module goes. And now we'll edit usercustomize.py in that directory. Here I import WinUnicode Console, and then I call the enable function. Let's give it a try. WinUnicode Console also works in Python 2, and the procedure for installing and enabling the package are the same as in Python 3. Hopefully the two items I've discussed in this video will prove helpful if you are working in Windows. In this video, we'll look at the topic of character encoding. The goal here is to offer some historical background on ASCII and various other character encodings that were devised prior to Unicode. The material in this video will provide a foundation for better understanding the problems that Unicode is meant to solve and how it does so. At the basic level, users are concerned with characters. Computers, on the other hand, work with binary data. A character encoding is a way of bridging that divide by providing a mapping between characters and bits. There is, however, no natural or default way of setting up such a mapping. Which characters should be included in the mapping? What values should the characters get? There are many ways of doing this, and so we end up with a wide variety of character encodings. An early and widespread character encoding was the American Standard Code for Information Exchange, ASCII. ASCII is a 7-bit encoding. It maps characters to the numbers 0 through 127. ASCII includes various control characters, punctuation, symbols, and numerals, along with uppercase and lowercase Latin letters. In this table, you can see the printable characters in the encoding, arranged according to their numerical value. Once 8-bit computer systems became common, the extra bit made it possible to add an additional 128 characters, in the 128 to 255 range. This is depicted on the table to the right. Various encodings were developed in order to take advantage of the extra space, to include characters that were not a part of ASCII. In the upper range, from hexadecimal 80 to FF, one could include, for example, accented Latin characters, symbols of various kinds, characters from non-Latin alphabets, such as Greek and Cyrillic, and so forth. These 8-bit encodings are sometimes called extended ASCII. The number of possible characters is double that of ASCII, but the total is still quite limited. Accordingly, numerous such encodings were developed to meet the needs of different users, usually to accommodate one's language or locale. Now let's take a look at some common 8-bit encodings, which can serve as illustrative examples. To the left, we see the table for Latin 1, or ISO 88591. This encoding extends ASCII to support most Western European languages. To the right, we see a very similar encoding table. This is CP1252, which is the default encoding on Windows. It is also sometimes referred to as ANSI. This encoding is a superset of Latin 1. Here we can see that additional characters have been added in the 80 to 9F range. On the left, we now have the table for Mac Roman or Mac OS Roman. This encoding was commonly used on Mac OS prior to OS X. It too provides support for Western European languages. As you can see, the character set is very similar to that used by CP1252, but the mappings for the non-ASCII characters are almost entirely different. Finally, for some examples of 8-bit encodings that support non-Latin alphabets, we have ISO 88597 for Greek, displayed on the left, and KOI-8R for Cyrillic, on the right. Now, there are numerous limitations and problems with these kinds of character encodings. We've already mentioned that 256 characters is quite restrictive, particularly when one has already used up the first 128 characters for ASCII. Languages and scripts that use a larger range of characters cannot be made to work within the limitations of simple 8-bit schemes. This is a problem, for example, with Chinese, Japanese, and Korean. Another problem with these encodings is that they map characters to specific bit patterns. Depending on the encoding in use, the same bit pattern can represent different characters, and the same character can be represented by different bit patterns. Take, for example, an E with an acute accent mark, such as you might find in the word cafe or resume. Here we have a side-by-side comparison of CP1252 and Mac OS Roman. In CP1252, E with acute accent is mapped to hexadecimal value E9, but in Mac OS Roman, the same character is mapped to value 8E. I'll create a new file now containing just the word resume. And now I'll save it in two different encodings, CP1252 and Mac Roman. Now that the files are saved, let's compare their contents using the xxd command. Here we can see the differences in how the E with acute accent is encoded. In the CP1252 encoded file, E with acute accent has value E9. And in the Mac OS Roman encoded file, the character has value 8E. Because of these incompatibilities between encodings, you must know the right encoding for your data. Otherwise, the binary information will be misinterpreted and you'll get back the wrong text. This is a crucial point. From the data alone, you cannot know for sure what the proper encoding is for that data. However, by inspecting the data, you can make informed guesses. This is what the Python chardet module and the corresponding char_detect command do, for example. In the files we were just looking at, there's not much data for char_detect to analyze, so the results are not what we would want to see. Both files are considered ISO 88592, which is an encoding used for Eastern European languages. Web browsers frequently have to guess at encodings. For example, when the encoding of an HTML document is not specified by the web server, nor indicated in the document itself. Let's see how Chrome handles the text files we just created. I'll open our resume files in separate tabs. Here is the version that was encoded in CP1252, and here's the version that was encoded in macOS Roman. As you can see, Chrome failed to render either file correctly. But if we override Chrome's encoding auto-detection and tell it which encodings to use, the correct text will appear. We'll set this file to Windows 1252 or CP1252. And now the text appears properly. And we'll set this file to the Macintosh encoding. And here too, the word appears correctly now. With the 8-bit encodings that we've been considering, one further limitation should be clear by now. Given the limited range of each encoding and the fact that their mappings overlap and are often inconsistent with one another, you cannot mix encodings in the same file or data stream. So, if you wanted to have a single file containing both Greek and Cyrillic, you would not be able to do so. Here's a short example. I have two files. One contains my name in Greek, the other contains my name in Cyrillic. The Greek version is encoded in ISO 88597, and the Cyrillic version is encoded in KOI8R. Let's use the icon utility to dump the contents of each file to the console. And let's see how well char detect handles these files. That looks good. Both encodings were correctly detected. But what if we tried to combine these files together? Char detect isn't so sure about this new file's encoding. Let's try examining the contents of the file again using iconv. If we try ISO 88597, the Greek comes through, but the Cyrillic does not. And if we try KOI8R, the Cyrillic comes through, but the Greek does not. By the way, if we were to try something else like Latin 1, both the Greek and the Cyrillic would be lost, and neither would come through properly. As we've seen, there are many pitfalls and limitations associated with older character encodings, such as the ASCII-based 8-bit encodings that we've been looking at. These problems occur even if one is working within a single character set, as we saw with the resume example. And things become considerably more difficult if one is working in a multilingual environment or dealing with multilingual data. Thus, a more powerful and less error-prone encoding system is needed, and as we will see, Unicode offers a good solution to these problems. This video provides a basic overview of Unicode. We will look at how Unicode addresses the limitations of earlier encoding schemes. We will also discuss the central concepts and terminology that will help you work effectively with Unicode text. Unicode is a complex standard, and there are many details and nuances that lie outside the present scope. Here I will highlight what I take to be the most important parts of the standard, and if you would like additional clarity on anything that is discussed here, I highly recommend checking out the unicode.org website, where you can find a wealth of helpful information, as well as the latest version of the Unicode standard. One of the chief goals of Unicode is to provide a universal character encoding. Prior to Unicode, one had to deal with a multitude of encodings, which were designed for specific languages and uses. For any textual data, you had to know the proper encoding for interpreting that data. Otherwise, you would get back corrupted or incomprehensible text. Unicode, by contrast, provides a single encoding, which can be used universally. The goal is to make it possible to encode any written language in the world, contemporary or historical, while also leaving plenty of room for any future needs. How does Unicode accomplish this? First, it removes the space limits of other encodings by providing a much wider range of numbers onto which characters can be mapped. There are well over 1 million numerical values available for character assignment. Furthermore, Unicode maintains a clear distinction between character values and their binary representation. Characters are mapped to numbers or code points, but how those numbers are stored in memory or on disk or transmitted over the network is regarded as a separate issue. For that, Unicode defines various encoding forms and schemes, which are also known as Unicode transformation formats. Another major part of Unicode is the character database. The database includes useful metadata about each character, the character's name, its category, as well as a number of other significant properties having to do with the character's meaning, appearance, behavior in certain contexts, relationship to other characters, and so forth. Let's now consider some of the key terms and concepts involved in Unicode. Unicode maps each character to what is called a code point. A code point is a non-negative integer, and code points can range from 0 up to the hexadecimal value 10FFFF. This means that there are 1,114,112 possible code points. Some code points are reserved for special uses, but the majority are available for character assignment. As of this recording, the latest version of the Unicode standard, version 8.0, includes over 120,000 characters. After assigned, reserved, and special use code points are removed, over 3/4 of the code point space remains unallocated. Thus, there's plenty of room for future growth. When referring to code points, we typically use the notation U plus the code point value in hexadecimal format. Here we see some example characters, the code points to which they are assigned, and their Unicode names. When thinking about code points, one should keep in mind that they are an abstraction. They are simply numbers, and they are distinct from any binary representation of their numerical values. To convert between Unicode text, which is a series of code points, and a binary representation of that text, which is a series of bytes, you use a character encoding scheme. Some of the schemes defined in the Unicode standard are UTF-32, UTF-16, and UTF-8. To be more precise about it, Unicode draws a distinction between character encoding forms and character encoding schemes. A character encoding form maps from code points to code units, while a character encoding scheme serializes the code units into bytes. In practice, however, it is common to refer to the combination of character encoding form and character encoding scheme using the term character encoding or the term character encoding scheme. For now, we won't delve into the details of how these encoding schemes work. Instead, let's take a look at two examples, which will suffice to show the distinction between code points and their binary representations. Here we see the results of encoding the lowercase Greek alpha according to each scheme. For simplicity's sake, I've shown just the big-endian variants of UTF-32 and UTF-16. UTF-32 always uses 4 bytes per character. In this example, however, UTF-16 and UTF-8 only use 2 bytes each. While UTF-32 and UTF-16 appear to straightforwardly encode the value of the code point, we can see that something different is happening with UTF-8, where we find CEB1 instead of UTF-16's 03B1. Now we have a character whose code point is beyond the 16-bit range. UTF-32 still uses 4 bytes to encode the character, but now the other two schemes use 4 bytes as well. This shows us that both UTF-16 and UTF-8 are variable width encodings. Furthermore, in UTF-16, it is no longer apparent at a glance how the code point information has been stored. An explanation of how each scheme operates and the relative advantages and disadvantages of each will be reserved for a separate lesson. Now let's take a look at how code points are organized. At the broadest level, groups of code points are divided into planes. Each plane contains 65,536, or 2 to the 16th, code points. There are 17 planes total. The first plane, or plane 0, is known as the Basic Multilingual Plane, or BMP. The remaining planes, planes 1 through 16, are called the supplementary planes. In general, the BMP contains the most commonly used characters, while less frequently used characters are found in the supplementary planes. Within planes, contiguous groups of code points are organized into what are called blocks. Although blocks group together characters based on language, script, function, meaning, or other properties, one should not assume too much from a character's block assignment. For the most part, blocks serve as a convenient way of dividing up the code space. Unicode concerns itself with characters. The term character can be confusing because it is used in many ways. According to the Unicode standard, one meaning of the term character is the smallest component of written language that has semantic value. Yet it is not necessarily the case that such base components correspond one-to-one to Unicode code points. In a programming context, it is common to think of characters and code points almost interchangeably. In other words, one uses the term character to refer to those units of writing that are assigned to code points, what are called coded characters or encoded characters. One thing to keep in mind about characters is that they are distinct from their visual representations. A character may have a basic shape associated with it, but it remains abstract. When a character is drawn or otherwise rendered, it can take on various visual forms. The visual representation of a character or group of characters is called a glyph. Unicode doesn't concern itself with glyphs. That is instead the responsibility of the font and the text rendering software. Here we see some glyphs of the lowercase a character. The letter can appear with a single-story shape or a double-story shape. It can have serifs or it can lack them. It can be made to look more like handwriting, and so on. In this case, the visual differences depend on the font. Characters can also change appearance based on the context in which they appear. For some writing systems, this is very important. Take, for example, the Arabic script, where many letters take on different shapes depending on whether they are joined to the preceding and following letters. The table here shows 2 such examples. A further complication is that there can be multiple ways of producing the same glyph. Usually this happens because of combining characters. Combining characters are not rendered independently, but are instead attached to some base character. Combining characters can be accents, diacritics, vowel points for languages like Hebrew and Arabic, and so forth. For example, here are 2 ways of producing a Greek eta with a rough breathing mark. The first way involves a single character, which includes both the letter and the diacritic. This is known as a precomposed character. The second way involves 2 separate characters, one of which is a combining character. The base character, the eta, comes first and is followed by the combining character, the breathing mark. A base character can be followed by more than one combining character. In its visual presentation, a combining character connects to the base character or is somehow positioned relative to it. The specific behavior depends on the characters that are involved, and this is an issue left to the font and the text rendering software. In this example, the combining character is drawn directly above the base character. From the user's standpoint, these are the same character, Ada with a rough breathing mark. The glyph that is produced is also the same, but the underlying code points are different. Therefore, it's possible to have two Unicode strings that are identical in appearance and meaning, but which are not equal to one another from a programming standpoint, where code points would be the basis of comparison. This has important consequences for many standard string operations, matching, comparison, sorting, and so on. To help deal with such cases, Unicode has the notion of equivalent sequences, and it defines several normalization forms, which can be used for string comparisons. Unicode also provides the Unicode collation algorithm, which is used to help with sorting. All of these will be discussed in greater detail elsewhere. Now we'll take a look at one final component of Unicode. This is the Unicode Character Database, or UCD. The database contains information about a wide range of character properties. For a given character, it includes such information as name, general category, casing, script and block, normalization properties, and so on. There are many other character properties beyond these that are recorded in the database. When working with Unicode text, the information provided by the Unicode Character Database can be extremely useful, for example, for text comparison and normalization. Various libraries provide interfaces to the database, such as Python's Unicode Data module. As I mentioned at the outset, there are many details and distinctions that I have necessarily glossed over, and instead I have focused on what I think is most relevant from a programming perspective. If you wish to pursue any of this further, once again I recommend looking at the many resources available on the Unicode website. In this video, we will look at the various ways of representing Unicode text in binary. For this process, Unicode defines various character encodings, or character encoding schemes. Let's begin by looking at some key terms and concepts. Unicode text consists of code points, which are simply numbers. These can range from 0 to hexadecimal 10FFFF. When talking about code points, we are not thinking about any binary representations of the code point's numerical values. Code points are just numbers. Accordingly, text can be thought of abstractly as consisting of sequences of numbers. In order to store, transmit, or otherwise use Unicode text on a computer, however, you need to convert the text to some binary representation. There are various ways of doing this, but in general there is a two-step process as we move from code points to bytes. First, code points are converted into what are called code units. A code unit is the minimal bit combination that can represent a unit of encoded text. The size of a code unit varies depending on the encoding that's being used. In some cases, a sequence of more than one code unit may be required to represent certain characters. The mapping of each code point to a sequence of code units is done through what is called a character encoding form. Next, code units are converted to bytes. To serialize sequences of code units into bytes, one applies a character encoding scheme. This is the more precise description of how the encoding process works, but in everyday usage, we typically talk about it as a single process, and for that we can just use the term character encoding. It's also possible to take the term character encoding scheme and apply it more generally to the whole process, not just the byte serialization of code units. In this video, we will look at the standard Unicode character encodings, UTF-32, UTF-16, and UTF-8. UTF stands for Unicode Transformation Format. Each one of these encodings defines an algorithm for converting between code points and byte sequences. Our main concern here is UTF-8, but we will begin with a quick overview of UTF-32 and UTF-16. After that, we will move on to a more detailed discussion of UTF-8. Okay, let's take a look at UTF-32. This is a simple, straightforward way of encoding Unicode text. Each character gets 4 bytes or 32 bits. That is to say, characters are stored in code units of 32 bits. Contained in each 32-bit code unit is the character's code point. According to the Unicode standard, code points go up to hexadecimal 10FFFF, or 21 bits, so each 32-bit code unit can comfortably hold any possible code point. By the way, this encoding is closely related to UCS4, so be aware that you may see the terms UTF-32 and UCS4 used interchangeably. Here we have a file containing a single Greek alpha. A lowercase alpha has code point 03B1, which we can confirm here by using vim's GA command. Now let's convert the file to UTF-32 using the iconv tool. And now let's examine the hexadecimal dump of the file. Here I use the XXD tool and I request 4-byte groupings in order to better show the individual code units. For now, ignore the first unit with value FEFF. This is the byte order mark, which we'll discuss shortly. Also disregard the third unit with value A. This is simply the new line at the end of the file. The important part here is the second unit, which encodes the alpha with value 03B1. I'm ignoring the issue of byte order for now, but basically UTF-32 is a fairly simple encoding. The major drawback of UTF-32 is that it wastes space. Depending on the type of textual data that you're working with, it can consume up to 4 times as much space as other encodings. Now let's move on to UTF-16. As the name suggests, UTF-16 is a 16-bit or 2-byte encoding. For code points that can fit within 16 bits, that is to say code points in the basic multilingual plane, the value of the code point is encoded directly in a single 16-bit code unit. Let's compare UTF-16 with UTF-32 using the same example from earlier. We begin by converting the file containing the single Greek alpha, and we then check the result. And there in the second byte grouping, we see the alpha with value 03B1. By comparing this with the UTF-32 version that we just looked at, you can see that, at least in this example, UTF-16 is much more space efficient. But what if the text includes characters with code points above FFFF? That is to say, code points that are located in one of the supplementary planes, beyond the basic multilingual plane. UTF-16 solves this problem by using what are called surrogate pairs. The code points from D800 through DFFF have been reserved as surrogates. For code points above FFFF, UTF-16 encodes the value by combining a high surrogate with a low surrogate. The high surrogate comes from the range D800 to DBFF, and the low surrogate comes from the range DC00 to DFFF. The two surrogates combined represent a single code point. The high surrogate encodes the upper 10 bits of the code point, and the low surrogate encodes the lower 10 bits of the code point. I won't go into details of the conversion algorithm here, but let's look at a simple example to get a basic sense of how this works. Let's begin by creating a file that contains the ace of spades character, which is assigned to code point 1F0A1. I've typed in the character, and now we can confirm the code point. And there it is, 1F0A1. This code point is located in plane 1, or the supplementary multilingual plane. It is not in the basic multilingual plane, and it cannot be encoded in a single 16-bit value. Now let's save this file and return to the terminal. By default, my editor saves the file as UTF-8. Let's use iconv again to convert the file to UTF-32 and UTF-16. And now let's compare the contents of those files. In UTF-32, we see the character here. But in UTF-16, we instead see the surrogate pairs. Whereas in UTF-32, the value of the code point is transparently visible, in UTF-16, it's a little bit more difficult to tell what's going on. One complication with both UTF-32 and UTF-16 is that you have to pay attention to byte order, or endianness. The endianness of an encoding scheme determines how the bytes within each code unit are to be arranged. This table shows the differences between big endian and little endian byte order for both UTF-32 and UTF-16. I've chosen the example character Latin capital letter A with breve because its code point 0102 helps illustrate the byte order more clearly. In their big endian versions, these encodings put the most significant bytes first, while in their little endian versions, they put the most significant bytes last. In order to help out in situations where the byte order is not known, a special character can be inserted at the beginning of a data stream. This character is known as the byte order mark, or BOM, and it has code point FEFF. We encountered this character earlier in this video when we compared the UTF-32 and UTF-16 serializations of the Greek lowercase alpha. You can't misinterpret a BOM by reading it in reverse order, because code point FFFE is a non-character. Therefore, if you have encoded textual data that begins with any of the 4 byte sequences in this table, you can make a reasonable guess about the data's encoding. However, this would still be a guess, and there would remain the possibility, albeit a very remote possibility, that the data is actually in some other encoding. We'll pause here for the moment and pick things up in the next video with a detailed look at UTF-8. Picking up where we left off, we'll now resume our earlier discussion of Unicode encoding schemes. As it turns out, the earlier descriptions I gave of UTF-32 and UTF-16 were simplifications, in which we assumed big endian byte order. There are actually several encoding schemes defined by the Unicode standard. Here we see a list of schemes showing their byte order and their use of the BOM. 4 of the schemes indicate byte order: UTF-32BE, UTF-32LE, UTF-16BE, and UTF-16LE. Data that has been tagged or otherwise marked as being encoded with one of these schemes should not use the BOM. With the UTF-32 and UTF-16 schemes, on the other hand, The endianness can go either way, and so it is permissible to use a BOM and probably a good idea to do so, unless you have some special reason to leave it out. As for UTF-8, this is a byte-oriented encoding, so there is no need for a BOM. Even so, it can be used, in which case it can help identify the data as being encoded in UTF-8. So far, we have a basic sense of how UTF-32 and UTF-16 work, and an awareness of the issues involved with byte ordering. Now let's take a look at UTF-8. UTF-8 is a popular and very widely used encoding, and it has many advantages. For these reasons, it's worth taking a closer look at its properties and seeing how it works. UTF-8 uses code units of 1 byte, but it is a variable width encoding. The number of bytes used to represent a single code point can vary. Depending on the code point, anywhere from 1 to 4 bytes might be needed. As was just mentioned, because UTF-8 is byte-oriented, byte order is not an issue, and the inclusion of a BOM at the beginning of a data stream is optional. If a BOM is present, it is encoded as a 3-byte sequence, EFBBBF. Single byte sequences in UTF-8 are used to represent the first 128 code points, which are the code points that correspond to ASCII. This is what makes UTF-8 backwards compatible with ASCII. A text encoded in ASCII would look exactly the same when encoded in UTF-8. Let's take a look at how UTF-8 encodes each code point. This table shows the bit layout for each of the possible byte sequence types, that is, the layouts for sequences of length 1, 2, 3, and 4. In the first 2 columns are the code point ranges and the number of bits that are encoded by each sequence type. The remaining 4 columns show the possible bit layouts. Byte 1 is called the leading byte. Every well-formed UTF-8 sequence must begin with one of these bit patterns. Either the high bit is a 0, or else the high bits consist of 2, 3, or 4 leading 1s followed by a 0. Bytes 2, 3, and 4, if present, are called the trailing bytes or continuation bytes. For these bytes, the high bits are always a 1 and a 0. In this table, the high bits that mark the sequence patterns are colored in red. The X's, which are colored in green, indicate the bits in which the actual code point value is stored. As we look at this table, here are some observations about the encoding scheme. To begin with, if the high bit is not set, then you have a single byte sequence. The characters represented by these sequences match ASCII exactly in both the range that they cover and the bit sequences that are used. This is how UTF-8 achieves backwards compatibility with ASCII. If, on the other hand, the high bit is set, you know you are somewhere in a multi-byte sequence. The byte that you are looking at must be either a leading byte or a continuation byte. It is easy to distinguish between leading and continuation bytes in multi-byte sequences because leading bytes have at least the first 2 high-order bits set. Continuation bytes, on the other hand, always begin with a 1, 0. In leading bytes of multi-byte sequences, the number of high bits that are set indicates the number of bytes in the sequence. So 110 begins a 2-byte sequence, 1110 a 3-byte sequence, and 11110 a 4-byte sequence. Each byte sequence must follow one of the 4 patterns that we see here, otherwise it is considered ill-formed. And finally, when encoding a code point, you must use the shortest sequence length possible. This means that there is only one valid byte sequence for each code point. Here we have one example character for each sequence type. Each character's code point is given in hexadecimal and binary. As before, red is used to indicate the bits that mark leading and continuation bytes. Green and blue are used to help show how the bits representing the code point value are distributed within the byte sequences. The basic process works like this. For a given code point, you set up a sequence of the length necessary to hold the code point's value. The bits representing the code point, which are the green and blue bits in this table, are then slotted into the lower bits of each byte, which are available for storage. The bottom example here, with a non-BMP character, shows that a 4-byte sequence in UTF-8 is capable of storing up to 21 bits of information, which is enough for any possible code point. Now that we've seen how UTF-8 works, here are some concluding observations. To begin with, some features of UTF-8 we've already noted. First, because the encoding scheme is byte-oriented, one does not have to worry about byte order, and the inclusion of a BOM is unnecessary, though permissible. And second, UTF-8 is backwards compatible with ASCII. In other words, it possesses ASCII transparency. Now, what about UTF-8's efficiency? When it comes to memory use, ASCII transparency means that UTF-8 is very efficient for text that is ASCII only or predominantly ASCII. It is also fairly efficient when dealing with European and Middle Eastern scripts. UTF-8's use of space breaks down as follows. 1 byte is needed for ASCII. 2 bytes are needed for most of the characters in European and Middle Eastern scripts. 3 bytes at most are needed for code points in the BMP, and 4 bytes are needed for code points beyond the BMP in the supplementary planes. Thus, UTF-8 is always more space efficient than UTF-32, given that UTF-32 always uses 4 bytes for each code unit. And depending on the type of text, UTF-8 can be more efficient than UTF-16. Keep in mind also that many text formats, such as XML and HTML, will contain a substantial amount of ASCII for the markup, regardless of the characters used in the actual content. This gives UTF-8 a further edge over UTF-16. Here's another advantage of UTF-8. Because it has ASCII transparency and is byte-oriented, software that was originally designed to use ASCII or ASCII-based 8-bit encodings can much more easily be adapted to use UTF-8 as compared to UTF-16 and UTF-32. There's another nice feature of UTF-8 when it comes to sorting. If Unicode strings are sorted by code point and their corresponding UTF-8 encoded bytes are sorted by binary order, the results will be the same. There are some disadvantages, however, when it comes to variable width encoding such as UTF-8. For example, normal indexing and slicing of UTF-8 encoded data is not possible. Nevertheless, you should probably avoid doing direct manipulation of UTF-8 bytes anyway. Instead, it's almost always going to be easier and safer to begin by decoding the bytes to Unicode strings or character strings, then to do all your work with these strings, and finally to encode everything back to UTF-8 bytes when you're done. In addition to what's been mentioned so far, UTF-8 has the added advantage of widespread adoption. To begin with, it is nowadays the default encoding on many operating systems, such as macOS X and many Linux distributions. Although Windows remains a notable exception where the situation with default encodings can be rather difficult to deal with. UTF-8 is also the preferred encoding for the web, as well as for many data formats, such as XML, HTML, CSS, and JSON. The World Wide Web Consortium recommends its use, and surveys and analysis of websites show that it is by far the most used encoding. In short, UTF-8 has become the de facto standard for encoding Unicode text. If you have the choice and don't have good reasons to do otherwise, you really should be using UTF-8 for data storage and transmission. When working with Unicode data, you're bound to encounter these schemes, particularly UTF-8 given its prevalence and special features. Accordingly, it's worth having some understanding of how these schemes work and an awareness of their relative advantages and disadvantages. In this video, we will look at string types in Python, and the distinction Python maintains between actual Unicode text and text that has been encoded into bytes. The most important point here, and the thing that can help prevent a lot of headache when working with Unicode in Python, is to always keep a clear distinction between text and bytes. In keeping with this distinction, Python provides 2 different string types, one for character strings or Unicode strings, and one for byte strings. The same distinction exists whether you are using Python 2 or Python 3, but the data types that are used are different. We'll start here by looking at how all this works in Python 3, and at the end of this lesson, we'll see how to apply the same principles in Python 2. In Python 3, the str type is used for Unicode strings. The bytes type, on the other hand, is used for any sort of binary data. Frequently, this binary data is encoded text. Let's begin by looking at Unicode strings and the str type, using the word resume as an example. A string literal is interpreted as Unicode text. You can use any of the usual quoting schemes. The text can be enclosed in single quotes, double quotes, or triple quotes. Starting in Python 3.3, you can also prefix the literals with a U. This is optional, and you really don't need to use this unless you are trying to maintain compatibility with Python 2. From this example, it's clear that you get the same result with or without the U prefix. In string literals, it's not always possible or convenient to insert Unicode characters directly. In such cases, there are 3 escape sequences that you can make use of. First, you can enter a character by its code point. If the code point fits into 16 bits, as is often the case, you use the \U escape sequence. The E with acute accent character has code point E9, so we can enter it as follows. Alternatively, you can enter a 32-bit code point value using the \U escape sequence. I'll use this to enter the same character, but typically you'd use this for characters whose code points cannot fit into 16 bits. Finally, instead of using the character's code point, you can use its name as found in the Unicode database. The escape sequence is \N, followed by the name in curly brackets. In this example, the character has name Latin small letter E with acute. We can confirm that all 3 methods yield the same result. Now let's move on to the bytes type, which is used to store binary data. As I mentioned earlier, this data is often encoded text, but really it can be any binary data. Ultimately, a bytes object is a sequence of integers, where each integer has a value from 0 up to 255. Bytes literals are similar to string literals, but they are prefixed with a B. To enter each byte's value, you use the \X escape sequence. This time let's use the word café. Let's see what its byte representation is if it is encoded in Latin 1. Here, echo produces the word cafe without a trailing new line, iconv encodes it into Latin 1, and then xxd shows the binary values in hexadecimal grouped by individual bytes. The bytes have hexadecimal values 63, 61, 66, and E9. Using these values, let's create a bytes object in Python. Notice how the representation of the bytes object presents the first 3 bytes as ASCII characters CAF. As it turns out, you can use ASCII characters in bytes literals as well. For bytes in the ASCII range, that is to say bytes with values from 0 to 127, Python uses the corresponding ASCII characters in both bytes literals and bytes representations. This is for convenience and clarity given the prevalence of ASCII-based binary protocols. In such cases, string-like behavior of bytes objects can be very helpful. For bytes outside the ASCII range, however, you need to use an escape sequence, such as \x, in your bytes literals. Attempting to include a non-ASCII character in a bytes literal will produce an error. So here you see that the E with acute accent could not be entered into the bytes literal. Now, when it comes to ASCII data, bytes objects look like and in some ways behave like character strings. You should, however, resist the temptation to think about these objects as text. Always keep in mind that bytes objects are binary data and should ultimately be thought of as sequences of integers. What we've seen so far is a quick introduction to Python's string types. Discussion of how to convert between text and bytes will come in a separate lesson. Let's look at the situation with string types in Python 2. An unfortunate complication is the incompatibility between Python 2 and Python 3 with regard to how their string types are named. Both Python 2 and Python 3 offer separate types for dealing with text and binary. The difference is that Python 2 uses Unicode objects for Unicode strings and stir objects for byte strings, whereas Python 3 uses stir objects for Unicode strings and bytes objects for byte strings. The differences are set out in this table. The main point of confusion is that the stir type stores binary data in Python 2, but Unicode text in Python 3. Without getting into the reasons for these differences, for now I'll just note that Python 3 fixes a number of issues with Unicode handling in Python 2, by making the primary string type fully Unicode capable, and also by establishing clearer boundaries between text strings and binary data. If you are working in Python 2, it can be very helpful to see how things work in Python 3 first, and to then apply the same concepts and practices to your Python 2 code. So for example, you would use Python 2's Unicode type for all character strings and reserve its stir type for binary data. Let's take a look at the syntax for string literals in Python 2. For Unicode strings, you must prefix the quotes with a U. In contrast to Python 3, this is mandatory in Python 2. The quotes can be single quotes, double quotes, or triple quotes. As with Unicode strings in Python 3, you can also use the \u and \U escape sequences to enter Unicode characters by code point, and the \N escape sequence to enter Unicode characters by name. If you leave out the U, what you get is a regular Python 2 string with type stir. Once again, avoid the temptation to use these objects as character strings. To help you keep things clear, you can use the B prefix following the syntax for bytes literals in Python 3. As you can see, the use of the B prefix doesn't change the result, but in addition to adding clarity, it will be useful later if you want to port your code to Python 3. One final warning. We saw earlier that if you try to include non-ASCII characters in a bytes literal in Python 3, you'll get a syntax error. A stir literal in Python 2, however, can include non-ASCII characters. You almost certainly do not want to do this because Python will convert these characters to some byte representation, and it might not do so in the way that you expect. Instead, you should use the \x escape sequence to enter byte values directly. Here's an example. For the implicit byte string, we just type in the accented E character directly. In the explicit byte string, we enter the byte value E9, which is the E with acute accent in Latin 1 and related encodings. But as we can see, the two byte strings are not the same. Let's see how the accented E is encoded in the implicit byte string. The character ended up as a 2-byte sequence, C3A9. This is because on my system I have WinUnicode console enabled, and this sets my input encoding to UTF-8. And in UTF-8, C3A9 is the byte sequence that represents the E with acute accent character. The larger point here is to avoid treating binary data types as text. This holds regardless of whether you are using bytes objects in Python 3 or stir objects in Python 2. As we will see, most of the time you should anyway be doing your work with proper Unicode objects, that is, stir objects in Python 3 or Unicode objects in Python 2. This way you can avoid the complications and pitfalls of working directly with binary data. In this video, we'll look at Python's facilities for converting between text and bytes. We will also look at the common errors that occur, how to interpret these errors, and how to handle them. Recall that Python provides distinct data types for text and bytes. In Python 3, text is stored in str objects, while binary data, which oftentimes means encoded text, is stored in bytes objects. To go between them, you need to specify an encoding or codec. There are numerous codecs available, but most codecs only handle a limited set of characters. If you want to make sure that you can handle any possible text, you should use one of the Unicode encoding schemes, UTF-32, UTF-16, or UTF-8. Given UTF-8 status as the de facto standard, that's what I'll default to here and elsewhere, but we'll also try out various other codecs in this video. The important terms here are encode and decode. Encoding is the process of going from text to bytes. Decoding is the reverse process, going from bytes back to text. To keep the terms straight, think of it from a human perspective. Text is that which is clear to humans, while binary data is opaque. Accordingly, we encode information from that which is more transparent to that which is more opaque. Thus, encoding is the process of converting text into bytes. Following the same principle, we decode information from that which is more opaque to something that is easier to understand, and so decoding is the process of converting bytes into text. Before we examine these processes in detail, let's take a quick look at two useful built-in functions. To find out a character's Unicode code point, you can use the OR function. It takes a one-character string as its argument and returns an integer. Let's start by looking at the A with umlaut character or A with diaresis as an example. This character's code point is hexadecimal E4. Another example would be the character with code point 1234. To perform the reverse operation, that is, to generate a character based on its code point, you can use the char or chr function. This function takes a numerical value and returns a one-character string. Let's do the reverse of the previous examples. By the way, if you're using Python 2, the char function is used to generate a byte string character, so it only accepts values from 0 to 255. If you want to generate a Unicode character, you would use the unichar function. Now let's take a look at how the encoding process works. We'll need some text to start with, which we will then encode into bytes. Let's begin by creating a sample stir object containing the word resume. The stir class has a method named encode. It takes two arguments, encoding and errors. Encoding lets you specify which codec to use. Errors lets you pick the error handler for any issues that arise in the encoding process. We'll talk about error handler shortly. For now, let's convert the text to a UTF-8 encoded byte sequence specifying the UTF-8 codec. We can be more concise and leave out the argument name. Also, the encode method defaults to UTF-8, so we can call it without any arguments and get the same result. Note here how the ASCII characters are represented directly in the resulting byte string. R, S, U, M. Each E with acute accent character, however, ends up as a 2-byte sequence, C3A9. So we can see it here and here. This is what we should expect, given that UTF-8 encodes characters beyond the ASCII range into multi-byte sequences. This means that you cannot expect the lengths of the character string and the encoded byte string to be the same. The Unicode string has 6 characters in it, but the encoded byte string has a length of 8. It's not crucial that you know the ins and outs of UTF-8, but we might as well take the opportunity here to review how UTF-8 works using the sequence C3A9. As you may recall, each byte sequence in UTF-8 begins with a leading byte, which is followed by up to 3 continuation bytes. Here, the leading byte begins with 110. The 2 ones tell us that this will be a 2-byte sequence. All continuation bytes begin with 10, which we see here. The actual code point value is stored in the remaining bits, which we see here and here. From this, we can reconstruct the code point value. And there it is. Hexadecimal E9 is the correct code point for this character, and we can confirm it as follows. Now let's return to our original string and try encoding it with an 8-bit ASCII-compatible codec. Here's the result if we encode the text as Latin 1. And here, E9 for the E with acute accent character is correct. Now let's try CP437, which assigns a different value to the E with acute accent character. And now we see that the character has hexadecimal value 82. What if the codec you're using doesn't support all of the characters in your text string? Unless you're using a Unicode encoding scheme, such as UTF-8, there's a very good chance that you'll run into this problem. In such cases, the encode method will throw a Unicode encode error. Here's an example. Let's take our resume string and try encoding it into ASCII. ASCII doesn't include the E with acute accent, so this is bound to fail. Let's unpack what's going on here. First, we see that this is a Unicode encode error. This means that we encountered a problem while converting Unicode text to a byte sequence, that is to say, while converting a str object to a bytes object. Next, we see the codec used for the conversion, which in this case is ASCII. Following that, we see the character that caused the problem with code point E9. Now let's try encoding the string using ISO 88597, which is used for Greek. This is an extended ASCII encoding, but it doesn't include the E with acute accent character. The stack trace looks a little bit different this time, but the problem is basically the same. The target encoding cannot deal with some character in the Unicode string that is being encoded. You can see the codec here, and the code point of the offending character is here. There are a couple of options for dealing with these errors. By default, the encode method uses the strict error handler, which raises a Unicode encode error if any sort of problem is encountered. If you use the ignore error handler, unencodable characters will be simply discarded. Obviously, this is less than ideal. You lose data and you cannot tell where the data was lost. The replace error handler at least lets you know where characters were discarded, but it still involves data loss. One way to somehow preserve the data is to use the XML char ref replace error handler, which will insert an XML entity for each unencodable character. The \replace and name replace error handlers work similarly, but they instead insert escape sequences for the unencodable characters. Ideally, you could avoid using these error handlers if your data is good and if you're applying a Unicode encoding scheme. But in reality, you may have to use a non-Unicode encoding scheme, and you cannot rely on your data to always be clean. And so you will have to make decisions about how to handle encoding errors. Now let's move on to decoding. In this process, we convert binary data into Unicode text. Let's set up an example byte string to work with, which contains the word cafe, encoded in Latin 1 or ISO 88591. Just as the str class has an encode method, so too does the bytes class have a decode method. It also takes two arguments, encoding and errors. These arguments have similar meanings, and once again they default to UTF-8 for the encoding and strict for the error handler. If we decode this byte string as Latin 1, we get our desired result. With decoding, you're less likely to run into errors because so many codecs can happily accept any given byte sequence. The danger is that of getting back garbage. If the wrong codec is used to decode the bytes, the resulting decoded text will be incorrect. For example, let's try decoding the same byte string using some other 8-bit ASCII-compatible encodings. In each case, the resulting decoded text is clearly incorrect. Something one sees frequently is UTF-8 encoded text that has been interpreted as Latin 1 or some other 8-bit encoding. As these examples show, it's essential that you use the right codec for your data. Frequently, no exception gets raised in the decoding process, so it may be a while before the erroneous decoding is noticed. At the same time, there are instances where a Unicode decode error will be raised. This occurs when the codec encounters unexpected bytes in the byte string. For example, the ASCII codec doesn't expect any byte with a value greater than 127 or hexadecimal 7F. Encoding schemes such as UTF-8 and UTF-16 expect their multi-byte sequences to follow certain patterns. If these patterns are not followed, a Unicode decode error will be raised. Consider the following Latin 1 encoded byte string. Here's what happens if we try decoding this byte string as UTF-8. Here we're told that the codec encountered invalid continuation byte. Let's take a closer look at what caused the problem. This byte starts with a 110, so according to UTF-8, it should be interpreted as the leading byte of a 2-byte sequence. Thus, the codec expects a continuation byte to follow, but instead it gets a byte corresponding to the ASCII letter R. Recall that UTF-16 uses surrogate pairs to encode characters beyond the basic multilingual plane. Big-endian UTF-16 would interpret the D8 as the first half of a 16-bit high surrogate. But no low surrogate follows, so an exception is raised. In these cases, the Unicode decode error is a good hint that you're using the wrong codec or that your data is somehow corrupt. If you're sure the codec is correct, you can again use error handlers to deal with the problems that occur. Similar to what we saw with the encoding process, there are ignore and replace error handlers for decoding. Again, you probably don't want to use the ignore error handler because of data loss issues. The replace error handler shows where decoding problems were encountered by inserting the Unicode replacement character, which has code point FFFD. There are additional error handlers that are more specialized in their use, but these are beyond the scope of this video. For details, refer to the official Python documentation, in particular the section on the codecs module. In this video, we'll see how you can use Unicode in your Python source files. Python can accept source files in various encodings. By default, Python 3 expects files that are encoded in UTF-8. Here's an example script that prints out some city names. We begin by assigning to the cities variable a list of str objects. 2 of these str objects contain non-ASCII characters. Then we print out each item in the list. The source file is encoded in UTF-8. If we try running it, we get the expected output. Now let's try running it in Python 2. And now we get a syntax error. The problem here is that Python 2 expects ASCII encoded source files by default. It does, however, have the ability to accept other encodings. In both Python 2 and Python 3, an encoding declaration can be included in the first or second line of the source file. Python will use this to determine how to interpret the bytes encountered in the file. There is some flexibility with the syntax of the encoding declaration, but basically you need to include the word coding, followed by a colon or equal sign, and then the encoding name. I'll now add an encoding declaration to the script. That's an acceptable way of doing it, but frequently you'll see an Emacs-style declaration, which looks like this. In any event, the script will now run correctly in Python 2. Now let's go back to Python 3 and see what happens if we declare the wrong encoding. The script runs, but the non-ASCII characters were not processed correctly. This happened because the Latin 1 codec has no problem processing whatever bytes it encounters in the file. Here, it took the multi-byte sequences in UTF-8 as consisting of separate characters. Let's save a new copy of the script, but this time we'll really encode it in Latin 1. And now we'll try running this new script. Now the accented characters in the string literal are properly interpreted, and we get the correct output again. At this point, we'll restore the proper encoding declaration in the original file to avoid any confusion. As you would expect, having your source files in a Unicode encoding scheme such as UTF-8 can be pretty convenient, because you can include the full range of Unicode characters in your code, and entering characters directly is usually easier and clearer than using escape sequences. Even though you have many encodings to choose from in your source files, it's best to stick with UTF-8 if at all possible. You should only use a different source file encoding if there's some special reason to do so. So far we've been looking at Unicode and string literals. Now let's talk about identifiers. In Python 3, identifiers are not limited to ASCII. For example, here are some variable names that include non-ASCII characters. Let's try making some changes to our example script. And now let's see if the script still runs with our new variable names. The output looks good, and Python handles the new variable names without any problem. Now, having identifiers with non-ASCII characters is an interesting feature, but in practice you should stick to ASCII-only identifiers. This will help ensure that a wider audience can make sense of your source code. In this video, we will discuss implicit decoding in Python 2. This is an area where Python 2's behavior differs significantly from Python 3, and it reveals something important about Python 3's string handling model, so it's a topic that deserves some attention. In this table, we see once again the string data types in Python 2 and Python 3. Python 2 uses Unicode objects for Unicode strings and str objects for byte strings. Python 3 uses str objects for Unicode strings and bytes objects for byte strings. The shift in meaning and use of the str type can be confusing. To briefly describe the reasons for this, the str type was originally used in Python 2 to store 8-bit text or binary data. Later on, the Unicode type was added to support proper Unicode strings. One of the main motivations for Python 3 was to improve Unicode handling. Not only did this mean changing the primary string type to be completely Unicode capable, but it also meant setting up a clearer separation between Unicode strings and byte strings. A big part of this was removing the Python 2 behavior of implicitly decoding byte strings into Unicode strings. Let's see how implicit decoding works. Let's say you are performing some operation that involves both a Unicode string and a byte string. In this case, Python 2 will attempt to decode the str byte string object to a Unicode object. In the decoding process, it applies the default codec or encoding, which is ASCII. Now, why is implicit decoding problematic? If you have a byte string that only contains ASCII characters, implicit decoding will work fine. But as soon as that byte string contains non-ASCII characters, implicit decoding will fail. This is why implicit decoding can be frustrating. Your script seems to be working just fine, and then all of a sudden you get a Unicode decode error. And this happens because non-ASCII characters ended up in a string that at some point gets implicitly decoded. Now we'll look at some examples showing how implicit decoding works. In these examples, we'll keep the Unicode string on the left and the byte string on the right. First, let's concatenate a Unicode string and a byte string. The stir object on the right is implicitly decoded into a Unicode object using the ASCII codec, and the result of the concatenation is a Unicode object. Here's another example involving comparison. A Unicode object is compared with a stir object. The stir is again implicitly decoded into a Unicode object using the ASCII codec, and this is why the equals returns true. You'll run into trouble with these kinds of operations, however, if the stir object cannot be decoded with the ASCII codec. For example, here we have a perfectly acceptable Python 2 stir object. But we'll get an error if we trigger implicit decoding. Nor would we be able to use this in a comparison. Now let's see what happens when we try these same operations in Python 3. Once again, in these examples, we'll keep the Unicode string on the left and the byte string on the right. I'm leaving up the Python 2 terminal so you can refer to it for comparison. First, let's try concatenating a Unicode string with a byte string. Python 3 won't convert the byte string for you. You'll have to do it yourself. Now let's try a comparison. Even though the strings appear to contain the same data, they are different types, and so Python 3 regards them as unequal. But once again, you could explicitly decode the byte string if you'd like. As for the café examples, these will fail for a different reason, because Python 3 is strict about not permitting non-ASCII characters in byte string literals. In conclusion, Python 3 requires you to perform your string conversions explicitly, even though there are many situations where Python 2's implicit decoding behavior can be very convenient. For example, if you know for certain that your byte strings will always contain ASCII. As we've seen, it can also be a subtle source of problems. In this video, we will look at a particularly confusing behavior with Python 2's string types, which is related to encoding and decoding. We know that byte strings have a decode method. This is what you use to convert the binary data to a Unicode string. What may come as a surprise, however, is that in Python 2, byte strings also have an encode method. Here's a sample byte string. It has a decode method, as we'd expect, but it also has an encode method. As we've already seen, the decode method produces a Unicode string. But what would the encode method do? Shouldn't the byte string already contain encoded text? Let's give it a try. So at least it returns a byte string. In this case, the string looks the same as the original. Two things actually happened when we called the encode method. First, Python attempted to decode the data variable to produce a Unicode object. It then encoded that Unicode object to give us our result. Things can get confusing when this behind-the-scenes decoding takes place. Let's see what happens if our byte string does not consist exclusively of ASCII. Not only did we get an exception when we called the encode method, but the exception we get is a Unicode decode error. This seems crazy if you don't know what's going on behind the scenes. You have to keep in mind that if for whatever reason you decide to encode a byte string, Python will first decode the byte string to a Unicode string before encoding it back to a byte string. When it tries to decode the original string, it will use the default codec, which is ASCII. So if your string contains non-ASCII bytes, you'll encounter a Unicode decode error. This behavior explains why the following example produces an error as well. We begin with a UTF-8 encoded byte string. But even though we have UTF-8 encoded bytes, calling the encode method with the UTF-8 codec will still fail. And this is because, as we've seen, a problem occurs in the intermediate decoding step, where the ASCII codec is used. This problem that we've been looking at also exists with Unicode objects. Sensibly enough, Unicode strings have an encode method to let you convert them to some byte representation, but they also have a decode method. Here's a quick demonstration. We'll start with a Unicode string. Encoding it works as we'd expect. Here we end up with a byte string of UTF-8 encoded bytes. But now let's try to decode the Unicode string. This will trigger a behind-the-scenes encoding operation using the ASCII codec. After that, the actual decoding will take place. And there, in the process of attempting to decode the string, we get a Unicode encode error. And this is because of the intermediate encoding step, where the non-ASCII character caused the encoding operation to fail. We've seen that attempting to encode a byte string or decode a Unicode string can produce confusing and unexpected results. You can avoid these problems by always being aware of whether you are dealing with text or bytes. That way you can make sure that you only encode text to bytes and that you only decode bytes to text. Keep in mind that this issue only exists in Python 2. In Python 3, the extra methods have been removed. Byte strings only have a decode method, and Unicode strings only have an encode method. In this video, I'll discuss some recommendations for working with Unicode in Python. These are general guidelines, but they should help you minimize Unicode-related problems and enable you to more effectively address such problems if they do occur. The main recommendation is to follow what is known as the Unicode Sandwich. But before we get to that, here are some basic principles for working with encoded text, which I think are worth following. The most fundamental point is to always keep text and bytes distinct. In Python 2, this is made more difficult by the fact that the primary string type is based on bytes. In both Python 2 and Python 3, it doesn't help that byte strings and Unicode strings share similar behavior and functionality. Nevertheless, you should always know what kind of string object you are working with. In Python 3, is it a str object or a bytes object? In Python 2, is it a Unicode object or a str object? A large part of keeping text and bytes distinct means always doing your conversions explicitly. Don't expect or rely on implicit conversion. This is more of a problem in Python 2, which attempts implicit decoding of byte strings to Unicode strings when the two data types come into contact. And finally, be explicit about your data's encoding. Whether you are encoding text or decoding bytes, always specify which codec to use. Typically, you should be using UTF-8. The Unicode Sandwich is a way of putting these principles into practice. This term was first coined by Ned Batchelder in his presentation on Pragmatic Unicode at PyCon 2012. The basic idea is this: when it comes to storage or transmission, you have to deal with bytes. In your program, you should decode bytes to Unicode as soon as possible. This means that all your actual work should be done with Unicode strings. And then you encode the Unicode back into bytes as late as you can when you finally send out or write out your data. So it's a sandwich with bytes on the outside and Unicode on the inside. This model helps minimize any confusion between text and bytes because you shouldn't be working with bytes of encoded text in the main logic of your program. Bytes should only occur at the very edges, when you read data in and when you push data out. In practice, many libraries and frameworks will actually take care of the decoding and encoding for you. In Python 3, your file objects can handle all decoding and encoding of text. You can get this behavior in Python 2 as well. Thus, in many cases, things are made simpler because the conversion work is taken care of for you. Nevertheless, it's good to keep in mind that you're still working within the sandwich model. In this video, we will look at file input and output with Unicode data and see how this fits within the Unicode sandwich model. Text that is stored in files must be encoded in some way. To work with it, we need to decode it to Unicode. According to the Unicode sandwich, we should decode the binary data as soon as possible. Then, when we have the text that we'd like to output to a file, we need to encode it to bytes. And if we again follow the Unicode sandwich, we'll encode the text as late as possible, right before we write it to our output files. Furthermore, we should know which encoding to use when decoding and encoding our data, and make that explicit in our conversions. Fortunately, Python 3 by default handles the conversions for us. If we open a file for reading, the file object will automatically decode the data and give us text. Similarly, if we open a file for writing, the file object will accept text and encode the data for us. Here we have a UTF-8 encoded test file that includes various Unicode characters. It contains samples from the well-known I can eat glass collection of phrases. In Python, let's open the file for reading. Here, it's essential that you specify the encoding. If you don't, Python will determine which encoding to use based on your OS and system settings. This is unpredictable and definitely not what you want to do. As always, you should be explicit about which codec to use. I specified read mode here, but that's actually optional, because it's the default mode anyway. Now, if we read from the file object, we get decoded Unicode text. Let's see what happens if we open the file for reading in binary mode. Here I've used the mode RB, and I no longer specify an encoding. Reading from the file object now returns binary data, or bytes. Here you can see that the returned data contains bytes of UTF-8 encoded text, which are taken directly from the file. Opening a file for writing works similarly. To have your Unicode text automatically encoded, you specify mode W and choose a codec. What you write to the file object must be text. Attempting to write bytes will result in an exception. But writing Unicode text works fine. Now let's try opening the file for writing in binary mode, using mode WB. As with reading in binary mode, you do not specify an encoding. In binary mode, the file object will not accept Unicode text. Bytes, on the other hand, are processed just fine. One further note about reading and writing in normal mode. Because the file object performs your decoding or encoding for you, you can also specify an error handler. This is passed as the errors argument to the open function. As you would expect, the possible error handlers are the same ones you'd use with the bytes.decode and stir.encode methods. handlers such as ignore, replace, and so forth. By letting your file objects do the decoding and encoding for you, you avoid having to deal with bytes and can do all your work with Unicode strings. Thus, it's easy to follow the Unicode Sandwich model. In this video, we'll continue our examination of file input and output with Unicode data by looking at an example script. Here we'll create a simple script that counts up character occurrences. It will take two arguments, an input file to analyze and an output file to store the results. For the input and output files, we'll use UTF-8 as our encoding. We'll call our script charcounter.py. First, we'll import the sys module as well as counter from the collections module. And here's the counter object that we'll use to keep track of character occurrences. And now we'll set up the basic script structure. In the main function, we first open the input file. Then we read in each line, and we update the counter using the contents of the line. Okay, let's give the script a test. It looks like it ran correctly, and now let's examine the output. Here we see the ASCII characters, then some extended Latin, some Greek, followed by Cyrillic, and finally at the end some more Greek. As you can see, the script does count the character occurrences, but the sorting didn't work properly. This can be fixed, and we will address sorting of Unicode strings in a separate lesson. Let's now see how all this works in Python 2. In Python 2, the built-in function open opens the file in binary mode. That's fine if you want to read or write bytes, but if you want similar behavior to Python 3's open function, you should instead use the open function that's provided in the IO module. Let's now adapt the charcounter.py script for Python 2. We'll make a copy of the script called charcounter2.py and edit it. The first thing to change are the calls to open. We'll import the IO module and in each instance call io.open. There's still more to do, but let's see what happens if we try to run the script. And here we've encountered an error. You may recall that Python 2 expects scripts to be in ASCII by default, but in this script I included a string literal with a non-ASCII character. We'll need to inform Python 2 about the source file's encoding, which in this case is UTF-8. Here's the character that caused the exception. It's the right arrow character with code point 2192. We'll add a comment and an encoding declaration at the top. And now the script runs. Let's give it a try. There's still a problem here, and it involves our string literals. In Python 3, these were interpreted as Unicode strings, but we need to make this clear to Python 2. So here on lines 17 and 21, I've indicated that the string literals should be interpreted as Unicode. Okay, let's try the script once again. And it works. Let's make sure the output is the same as with the Python 3 version. And that looks good. We've been looking at a fairly simple script here, but it does show how one would go about reading Unicode data from a file and writing Unicode data back out to a file without having to manually do all the conversions between text and bytes. We also saw how to transfer the same approach to Python 2 using io.open instead of the built-in open function. This also gave us the opportunity to review some of the other differences in Unicode handling between Python 2 and Python 3. And with that, we can conclude this video, in which we used an example script to demonstrate how one can do file input and output with Unicode data. The Unicode character database includes a great deal of useful character metadata. In this video, we will look at some ways of accessing and using this metadata in Python. Several bits of Unicode character information can be accessed through methods of the stir class. isAlpha tells you whether the string consists of alphabetic characters. The next three methods relate to numerals: isDecimal, isDigit, and isNumeric. It's not immediately clear how these differ based on their names. The key is to look at the Unicode categories they check for. isDecimal checks for decimal digits, or category ND. isDigit checks for decimal digits or other numeric characters, categories ND and NO. isNumeric checks for decimal digits or other numeric characters, or letter-like numeric characters. These are categories ND, NO, and NL. These three methods end up being pretty similar, but you may want to investigate the details of the Unicode categories in case the differences are relevant to your needs. And finally, isAlNum checks if every character in the string falls into one of the just mentioned categories. So those are the stir methods. But the primary way of accessing Unicode character metadata is through the Unicode data module. Let's look at some of its functions. Each of the first three functions listed here, name, category, and combining, takes a single character string as its argument. Name gives you the character's Unicode name. Category gives you the character's general category. And combining tells you the character's combining class. If the character isn't a combining character, the function returns 0. The lookup function will give you a character based on its name. If you don't provide a valid name, a key error will be raised. Here are some quick examples. First, we'll use the name function. Let's use the category function on the same character. And we see the result is LL. Let's now try the same with a combining mark. And here you see that the general category for the character is MN. Because this is a combining character, we can also find out its combining class. The combining class for the phi character that we looked at earlier, however, will be 0. Now let's try the lookup function. And here's what happens if we don't supply a valid Unicode character name. The normalize function is very important, but given the complexity of the topic, we'll have to look at it in a separate lesson. The Unicode data module has some additional functions as well. You can refer to the module documentation page for a complete listing, along with further details of the functions listed here. In this lesson, we will look at Unicode normalization, a procedure that is essential if you want to have reliable Unicode string comparison and matching. To make sense of normalization, we need a little background. I'll skip over some of the finer details and focus on what is necessary for practical use of normalization. For a fuller picture, you should consult the official Unicode documentation. First, there's the concept of an abstract character. An abstract character is a unit of information in textual data. It is not tied to a specific visual representation. Oftentimes when we talk about characters in a general sense, we're talking about abstract characters. An abstract character doesn't necessarily have a Unicode code point assigned to it. It may instead be represented by a code point sequence. In fact, there may be several code point sequences that represent the same abstract character. Here are some examples. The E with acute accent character can be represented by two sequences. The first option is the single code point 00E9, which has the name Latin small letter e with acute. And the second option is the two-character sequence, a small letter e followed by 0301, the combining acute accent. The FI ligature also has two possible sequences. The first option is the code point FB01, Latin small ligature FI. And the second option is simply to have an F followed by an I. Because an abstract character can be represented by different code point sequences, it's very possible for two Unicode strings to look the same and share the same meaning, even though they contain different sequences of code points. This means that at some point, we're going to run into trouble when we try to compare strings or search for matches within a string. Here we'll look at two possibilities for the E with acute accent character. The strings look the same, but we can confirm that they contain different code points. In order to help deal with these situations, Unicode defines two types of equivalence. Code point sequences are said to be equivalent if they represent the same abstract character. There are two types of equivalence. The first is called canonical equivalence. Code point sequences are canonically equivalent if they represent the same abstract character and if they produce the same visual appearance and behavior. The second is called compatibility equivalence. Here again, code point sequences represent the same abstract character, but differences in visual appearance and behavior are now permitted. And so compatibility equivalence is more flexible or looser than canonical equivalence. Let's take a look at some examples of canonical equivalence. Here's the E with acute accent character again, which we looked at earlier. For a more complex example, we have a Greek omega with a smooth breathing and a circumflex accent. There are three possible code point sequences to represent this character. The first sequence consists of a single precomposed character, 1F66. The second sequence consists of a precomposed character with the omega and smooth breathing, 1F60, followed by a combining character for the circumflex accent, 0342. And the final sequence separates out the three components. There's the omega, 03C9, then the combining smooth breathing, 0313, and then the combining circumflex accent, 0342. Remember, if code point sequences are canonically equivalent, then not only do they represent the same abstract character, but they also produce the same visual appearance and behavior. Here are some examples of compatibility equivalence. The FI ligature, FB01, has compatibility equivalence with a simple sequence of separate F and I characters. And the 1/2 sign, 00BD, has compatibility equivalents to the 3-character sequence 1/2. Let's take a closer look at the Greek example, where we have an omega with a smooth breathing and a circumflex accent. We'll compare the 3 possible code point sequences. Each string represents the same abstract character and has the same appearance and meaning. Nevertheless, the underlying code point sequences are different. Therefore, Python will not regard them as equal. Moving on to another example, consider the following string. Because of the FI ligature in the word fish and the combining accent in the word cafe, searching for these words in the string is less than straightforward. These tests fail because, despite the surface similarities, the underlying code point sequences do not match. Having discussed abstract characters and the 2 forms of equivalence, canonical equivalence and compatibility equivalence, we're now ready to talk about normalization. We'll pause here for the moment and pick things up in the next video with the rest of our treatment of this topic. Picking up where we left off, we'll now build off of the earlier discussion and talk about normalization. As we saw earlier, different code point sequences can represent the same abstract character or sequence of abstract characters. This presents a problem if we want to do string comparisons. Even though 2 strings might be equivalent based on their meaning or even their exact visual appearance, if the underlying code point sequences aren't the same, we won't be able to compare them properly. The solution to this problem is normalization. Normalization ensures that precomposed or decomposed characters are used consistently, and that combining characters are arranged in a set order. As a result, if you normalize your strings, you'll be able to compare them more reliably. There are 4 ways that you can normalize a string, or 4 normalization forms: NFC, NFD, NFKC, and NFKD. The first thing to do is to take note of the naming pattern. Each form ends in C or D, and 2 of the forms include a K. The C stands for composition, and the D stands for decomposition. The C forms alter the string to use composite characters where possible. The D forms, by contrast, break the composite characters apart into separate characters. The K stands for compatibility. Whereas NFC and NFD preserve canonical equivalence, NFKC and NFKD will replace characters with their compatibility equivalent forms. Let's take a look at the basic process used by each form. NFD simply performs a canonical decomposition, breaking apart composite characters to their canonical equivalents. NFC begins with a canonical decomposition, just like NFD, but after that it recombines characters to their composite forms. By the way, NFC is the normalization form that you should use by default for storage and transmission. If you're unsure about the consistency of your textual data, then normalize it with NFC before you do any work with it. Here we see the results of applying NFD and NFC to 2 words, schön and café. There are 2 versions of each word, one with precomposed characters and one with decomposed characters. Changes to the original string are highlighted here in red. As you can see, regardless of which version is used as the source string, we get the same results. NFD breaks apart the composite characters, and NFC combines them. Let's move on to the compatibility forms. NFKD performs a compatibility decomposition. NFKC begins with a compatibility decomposition and follows this up with a canonical composition. Note that the second step is a canonical composition and not a compatibility composition, and so it will insert precomposed characters where possible. Care should be taken when using NFKC and NFKD. Compatibility decomposition is a lossy process. It often involves the removal of formatting distinctions, such that the appearance and behavior of the original string might be altered in significant ways. In this table, we can compare all 4 normalization forms. Again, changes to the original string have been highlighted in red. The first string is ether, with an AE ligature. This ligature is unaffected in NFD and NFC, but the compatibility decomposition in NFKD and NFKC replaces it with separate A and E characters. The next string is fish sauté, with an FI ligature and a precomposed E with acute accent. The FI ligature is unaffected in NFD and NFC, but it is replaced by individual characters in NFKD and NFKC. The precomposed E with acute accent is decomposed in the D forms, NFD and NFKD. The third string is 8.5, using the 1/2 character. The string does not change in NFD and NFC, but in NFKD and NFKC, the 1/2 character is replaced by the sequence 1/2. And finally, we have 2 to the third, with the superscript 3 character. The compatibility decomposition in NFKD and NFKC converts the superscript 3 to a normal 3. As you can see, NFKD and NFKC can lose important formatting information, particularly with numerals. In these examples, 8.5 became 81/2, and 2 to the third became 23. On the other hand, these same normalization forms made it possible to do string comparison and matching with the ether and fish sauté strings. Based on what we've seen so far, here are some recommendations for using normalization. First, you should only use NFKD and NFKC for specific purposes, such as searching and indexing. You don't want to store text that has been processed with these normalization forms because you will lose information and might even corrupt the text's meaning. For general use, including storage, you should use NFC. A lot of software uses NFC by default, and it's the normalization form recommended by the World Wide Web Consortium. And one final related point, when processing new data, you should play it safe and normalize the data to NFC before working with it. Now that we've discussed the key concepts in normalization and seen what each of the forms does, let's see how you would go about normalizing strings in Python. The Unicode data module has a normalize function. It takes two arguments, the normalization form to apply, and an input string. Let's begin with a simple example. And now let's check the length of the string when normalized according to NFC and NFD. The NFD string is longer by one additional character because the precomposed O with umlaut or O with diaresis in the original string is replaced by an O and a combining diaresis. Here's another slightly more involved example. I've written the original string here to include a precomposed A with umlaut and an FI ligature. Now we will apply each normalization form to the string and see the resulting length. The NFC string has a precomposed A with diaresis and an FI ligature. The NFD string decomposes the A with diaresis to an A and a separate combining diaresis. Thus, the string length increases to 8. The NFKC string restores the precomposed A with diaresis, but it splits the FI ligature into separate characters, so it too ends up having length 8. And finally, the NFKD string decomposes both the A with diaresis and the FI ligature, and therefore it has a length of 9. Let's finish up here by seeing how we might use normalization in string comparisons. We'll write a short utility function that compares the NFC versions of its two input strings. Here's what happens if we try it on the E with acute accent. Now let's try the function on the Greek omega with smooth breathing and circumflex accent, which we saw earlier. We'll compare the string against the decomposed version. Now we'll test our utility function on these two strings. And it works in this case as well. Always be aware that you can't have reliable string comparison and matching without normalization. The form you use depends on your needs, but typically you will use either NFC or NFKC. Only use NFKC or NFKD for specific purposes, and because they introduce data loss, don't store your text in either of these forms. And finally, if you aren't sure about the consistency of the text that your program is getting, then make sure to normalize it with NFC before storing it or working with it. In this video, we will address another topic that is related to string comparisons and matching. This is case folding. We've seen that normalization is necessary to get some consistency between the various code point sequences that can be used to represent the same abstract characters. The other issue we have to worry about is case, because we typically want to do case-insensitive matching. The process of case folding will get strings into a comparable state. To apply case folding, you simply use the stir class's casefold method. This is actually very similar to using the lower method, but it does a few additional conversions. Here we have the German word for foot, Fuß. The final letter, which looks similar to a Greek beta, is an Eszett. Now let's compare the results when we call the lower and casefold methods. Here the lower method changes the initial f to lowercase, but it leaves the Eszett alone. The casefold method, however, does take the additional step of replacing the Eszett with two lowercase s characters. So, if you want to compare two Unicode strings, you should first normalize them. Typically, this means using NFC, but if you want to be more flexible, you can use NFKC. After that, apply case folding, and then you can compare the strings. In this video, we'll write a script to demonstrate how you would use some of the Unicode functions we've discussed so far. This script is based on a real problem. You have a piece of software that performs textual analysis of ancient Greek texts. The software only accepts text that contains Greek letters without the usual diacritical marks, such as breathing marks and accents. Digital texts typically include those marks, so it's necessary to find a way to strip them out, so that the texts can be used as input for the textual analysis software. As an illustration of the desired process, here's a snippet of ancient Greek text taken from near the beginning of Plato's Symposium. Here you can see the normally marked text, and then the same text with the marks removed. Before getting started with the script, let's take a quick look at the diacritical marks that are used for ancient Greek. In this table, we see how each diacritic looks when attached to a lowercase eta. First, there are two types of breathing marks, smooth and rough. Then there are three accents, acute, grave, and circumflex. Finally, some vowels can have what's called an iota subscript. At the bottom is an example demonstrating all three types of diacritical mark attached to the same vowel. It has a smooth breathing, a circumflex accent, and an iota subscript. This is an actual Greek word, a form of the verb to be. The script will take two arguments, an input file and an output file. Normal accented Greek is read in from the input file. All diacritics are stripped from the text, but otherwise the text is left unchanged. Then the altered text is written to the output file. To remove the diacritics, we will perform the following steps. First, convert the text to normalization form D. This will ensure that no precomposed character remains in the text, and that each diacritical mark is represented by a separate character. Second, identify and remove the diacritical marks. Third, convert the text back into normalization form C. There are a couple of ways to perform step 2. As we write our script, we'll try out two different ways. Here's our first attempt. We'll name the script unmark_v1.py. In this version, we'll use regular expressions to remove diacritics. We begin with the script's basic structure. In the main function, we'll open our input file and our output file, and we'll read in the input file one line at a time. For now, we'll just write each line back to the output file. Now let's implement diacritics removal. We'll do this in a function called unmark. First, we'll convert the text to normalization form D to replace all precomposed characters with their decomposed canonical equivalents. Next, we'll use a regular expression to remove all combining marks. The regular expression object is named marks_re. After that, we'll return the result normalized in form NFC. We still have to set up the regular expression object. All of the relevant marks are in Unicode block combining diacritical marks. This block extends from code point 0300 to code point 036F. We'll set up our regular expression to match anything in that range. As is evident from this example, regular expressions in Python can handle Unicode just fine. And now we'll alter our processing loop to call unmark on each line. Okay, the script now looks ready. Let's try running it on a test file. And now we'll run the script. So far so good. Let's see our output. As you can see, all diacritics have been removed, and otherwise the text is unchanged. Now, perhaps something doesn't feel quite right with the regular expression. In fact, we can take a different approach, discarding the regular expression and instead using a function from the Unicode data module. Let's create a new script, unmark_v2.py. First, let's get rid of the regular expression. In this new version, we'll instead use the combining function from the Unicode data module. The combining function takes a single character and returns the character's canonical combining class value. For combining marks, there are several possible values, all of them positive integers. But if the character is not a combining mark, the returned value is 0. We'll now use this function to filter out any combining marks. The script looks like a good improvement. It makes our intent clear, and it identifies combining marks more reliably. Let's try out the new version of the script. And now we'll make sure that the output was the same as before. That looks good. The two versions of the script produce the same output. We're not quite done yet. As it turns out, we actually want to preserve iota subscripts in our output. We'll create a third version of the script that implements this functionality. To begin with, let's create a helper function to determine if a character should be kept. Iota subscript has its own combining class value, 240. So if the combining class is 0 or 240, we'll keep the character. And now we'll update our unmark function accordingly. Note here the importance of normalizing the string in form NFC before returning it. This final step ensures that the iota subscripts are recombined with their base characters. Let's give this new script a try. And now we'll compare the results. To better show what changed, I'll use the visual diff program meld. Sure enough, the latest version of the script preserves the iota subscripts. In these three related scripts, we've seen some ways of applying Python's Unicode functions, specifically normalization and one of the functions used to access information in the Unicode character database. We also saw how Unicode can be used seamlessly with regular expressions in Python. In this video, we will look at a simple solution to sorting Unicode strings using the pyuca module. The default sorting functions in Python work fine for English strings, but they cannot handle multilingual strings properly. For example, here is a list of sample words. The words are senior, senator, neat, nest, nay, senor, and sentinel. Now we'll use the sorted function to see how these strings get sorted by default. The results aren't quite correct. Nay should come between neat and nest. Senor should come between senior and sentinel. If you think about it, sorting is a pretty complex task, and it becomes much more difficult when you're dealing with the full range of scripts and languages. Fortunately, Unicode supplies a general-purpose solution through the Unicode collation algorithm, or UCA. Included in the UCA is a table that defines the default collation order for all Unicode characters. The pyuca module, written by James Tauber, provides a Python implementation of the Unicode collation algorithm. The module can be installed with pip, and it works with both Python 2 and Python 3. Using the pyuca module is pretty simple. After importing the module, you create a new collator instance. You can then pass the collator's sort key method as the key argument to the sorted function. And there it is. The strings are now sorted properly, with nay and senor in their proper places. By the way, if we want to sort the list in place, we can follow the same procedure with the list's sort method. Here's the list, and now we'll sort it in place. And here are the results. And again, the results look good. Using pyuca, we can now fix the char counter script that we created earlier to have it sort its output properly. Here we're starting with a copy of the earlier script, but I've renamed it to charcounter_v2.py. First, we'll import the pyuca module. Then we'll create a new collator object. Now we can modify our call to sorted to use our collator object's sort key method. And now we can try out the updated script. If we examine the output, we'll see that the characters are now sorted properly. We start with some punctuation, followed by Latin letters. Here at the beginning, we see that accented characters are handled properly. Now let's scroll down to the next page. After the Latin letters come the Greek letters. Again, accented characters are handled properly, as we see here with these upsilon characters. I'll now scroll down to the end. The Greek letters end with the phi here, and after that we get Cyrillic letters. So as you can see, pyuca provides a simple and effective solution for the Unicode string sorting problem. Thank you for watching this course on working with Unicode in Python. In this video, we'll wrap things up, first by looking over the topics that we've covered, and then by reviewing the basic recommendations that have come up along the way. Recommendations that should help you avoid problems and work more effectively with Unicode. I'll also offer some recommendations for further reading or study, if you'd like to dig deeper into any of the topics that have been presented in this course. Let's look at what we've covered. We began with some background on character encodings. There are many limitations to earlier encodings, and we saw how Unicode addresses these issues. After going over the key concepts in Unicode, we then looked at Unicode encoding schemes to understand the common ways of converting Unicode text to bytes and back again. After that, we looked at the basics of string handling in Python. Python provides different data types for storing text strings and byte streams. We compared the types in Python 2 and Python 3, and we looked at the details of how one converts between text strings and byte streams. With these basics covered, we took a slightly broader view to see how the use of text and bytes should fit into the larger structure of your code. The main principle here was the Unicode Sandwich. We then focused on a very common case, that of file input and output, in order to see how one applies the Unicode Sandwich when working with Unicode data that is stored in files. When working with Unicode text, basic tasks like comparison and sorting become much more complex. Accordingly, we considered how you would handle some of these issues. We began by looking at ways of accessing the Unicode character metadata that is stored in the Unicode character database through various stir methods in the Unicode data module, and we then focused on the critical issue of normalization, which is essential for reliable text comparisons. After that, we looked at some examples of how normalization might be put into practice. Finally, we moved on to the issue of sorting. This can be tricky because of the wide range of characters in Unicode and the various rules for sort order in different languages, but fortunately the pyuca package makes things a lot easier. Along the way, I've offered some recommendations for working with Unicode. Let's review these once more. The first major principle is to keep text and bytes distinct. This means always knowing whether you are working with text or bytes, and always doing your conversions explicitly. The second major principle is the Unicode Sandwich, which dictates the following. When receiving data, decode from bytes to Unicode text as soon as possible, do your work with the Unicode text, and after that, encode from Unicode text to bytes as late as possible when you send out your data. There are a number of helpful resources out there related to Unicode and Python. Here's some good starting points if you want to dig deeper into any of the topics that we've covered. First, there's a wealth of resources at the Unicode Consortium website. Some of the documentation can get rather technical, but this is the authoritative source if you have questions or need more information on any Unicode-related topic. The Python Unicode How-To is concise yet helpful. It also contains some pointers to further reading. Note that there are separate versions of this document for Python 2 and Python 3. For details of the changes introduced in Python 3, as well as further discussion of Python's Unicode support, Nick Coughlin's Python notes are quite illuminating. Some very good practical advice is included in his articles. And finally, Chapter 4 of Luciano Jamalio's Fluent Python offers an excellent treatment of Unicode handling in Python. In addition, I highly recommend looking at his recommendations for further reading at the end of the chapter. In closing, I hope you found this course helpful, that it has demystified Unicode for you, and that it has equipped you with a solid foundation for integrating proper Unicode handling in your Python code. Thanks again for watching.